Hello, everyone. My name is Nicholas Mascarella. Today I'm joined by Catherine Cronin, David Moss, and Jonathan Ibanez. We are Team IGT, and our project was image processing from a camera-type device. The motivation for our project was IGT's current imagers have problems processing images in varied lighting and with obstructions such as shadows and wrinkles. It was our job to develop an Hdr algorithm that was completely proprietary, using no third-party sources, and using color balancing algorithms as well to produce the best possible quality image for these imagers. That was the best outcome for this project, as I mentioned, using this HDR and this color balance to produce the best images for IGT's imagers. And that's what we have achieved. So starting with our hardware consisted of an inverted tripod with a mounted camera and 2 strips of LED lights that we used to take pictures in varied lighting and with different obstructions, as I mentioned. And we used a network connection to transfer those pictures wirelessly to our computer using our flash SD card. Now I'm going to pass it to Catherine, who will continue talking about our accomplishments.
So last semester, one of our main accomplishments was the raw data extraction. The camera provides a raw image file, and the raw image file contains pixel data in bits, as seen above. The bits are then converted to integer values from 0 to 255, and it's displayed as a grayscale image, as seen in the bottom right. Next, I'm going to give you a little bit of background on Bayer filters. Bayer filters are arrangements of RGB, red, green, blue, light filters, and they're used in most consumer cameras. We assign each pixel a color according to the Bayer filter, and it can be seen in the bottom right. Next, we have to interpolate and fill in the missing color values. Each pixel only has one of 3 colors, red, green, or blue, and we use the neighboring pixels to derive the missing color values. Next, I'll show you a video of everything we've accomplished this semester. So first we load the image. This is our user interface. And we have energy HDRs and color filters. In the bottom right, left, you can see the histogram, and the tooltip shows the RGB value in numerical form. There's a color filter. Once we interpolate that, you'll see our final product. One second. And there it is. We just have to interpolate this final thing. We'll zoom in, and we have our final product. Thank you.
Now, as for our software accomplishments, our team was successful at developing and implementing a simple yet intuitive user interface to handle various image processing applications. So through our software, the user is able to transfer images straight from the camera itself to the computer to be processed by many algorithms that our team has developed, such as HDR or color balancing. Of course, the user is also able to zoom in and out of the images and is given the ability to save their image at any step during the process. Now, our software also comes equipped with a tooltip functionality, which shows the current pixel value for the pixel that's under the mouse cursor, which is a really useful tool to have when you're trying to debug some of the algorithms. And in addition, our algorithm also have a histogram feature, which is shown here at the bottom left. So the histogram contains the overall RGB value for the whole entire image, and can provide the user with some valuable information, such as what colors are missing when we're trying to color balance an image. Now let's talk about the main scope of our project, which is HDR, or high dynamic range. So today we hear the term HDR everywhere, whether it's the new HDR TVs on sale at Best Buy, or the HDR option you see when you open up the camera app on your phone. So the whole world is shifting towards HDR. But what exactly is HDR? Well, in essence, HDR, or HDR imaging, is a technique used in image processing to produce an image with a wider range of colors and luminance than otherwise possible. So as shown here by these 2 comparisons of the normal image and the HDR image. As you can see, the HDR image not only contains a wider range of colors, but the colors are also more vivid and has higher contrast. So how exactly is HDR imaging achieved? Well, at the most basic level, an HDR image is created by combining 2 or more images of the same subject captured at different exposures, as shown by this image and this image. Now, typically, you will want at least one overexposure and one underexposed image. because the overexposure can bring out details not present in the underexposure and vice versa. Now, after we obtain all the individual exposures, an HDR algorithm will then be used to extract the best information, the best detail from each of the individual exposures, and combine everything to form one single HDR image. And with that, I will now hand over to Jonathan, who will go further into detail in regard to some of the algorithms that our team has implemented.
So first, we're going to be going over the HDR algorithm that we developed this semester. As David mentioned, we want as much detail as possible in our high dynamic range images. We noticed that there was a correlation between contrast and detail. More detail in an area suggested that there was more contrast in that area as well. So we want to use contrast as our primary tool in developing our HDR algorithm. So we quantified contrast by looking at a pixel's neighbors in the Bayer pattern, as shown here. We got a contrast value by determining the difference between that pixel and its neighbors. So here we have the highest contrast value possible, and here's the lowest contrast value possible when all the pixels are the same. We were able to use these contrast values to implement an HDR algorithm. So our algorithm takes in a number of input images, in this case 2, but we could take in more than 2, and outputs a high dynamic range image. It does so by computing the contrast values of each of the images at a particular point. It then assigns a value to the HDR image, which is a combination of the input image values. However, it leans towards the values from images that have more contrast. So in this example here, we have image 1, which is a bright value, but no contrast. And here we have image 2, which is a dark value, but there's some contrast. Our HDR image will assign a darker value to that pixel because image 2 has more contrast. This technique is applied to every pixel in the image, and that completes our algorithm. So how does this work in practice? Here we have an overexposed and an underexposed image of the same subject. If we were to just average these two images together, we achieve this result. If we instead use our contrast-based HDR algorithm, we get this result. A side-by-side comparison makes it easier to see that our contrast-based HDR algorithm makes the ticket boxes stand out from the background more than a naive implementation would. After we were satisfied with the clarity of our images, we also wanted to work on the coloring as well. Different lighting setups will produce different colored images. We wanted to remove the color tint from our images. After researching in color theory, we found this task to be difficult, if not impossible, to achieve. But that didn't stop us from inventing an algorithm that takes advantage of the fact that the important bits of a ticket slip, such as the boxes, are always placed over a white background. So our color balancing algorithm is a whitening algorithm that looks at a region, determines the background of this region by the most commonly occurring color, in this case it would be green. It then changes the RGB values of all of the pixels in the region by the same amount until the background becomes white, as shown here. As a result, any outliers in the background, such as the ticket boxes, are also color corrected as a result. This technique is also applied to every pixel in the image. And here are our results. We have a ticket slip that is perfectly readable and is accurate in both color and detail. And now I'll take it over to Catherine, who will discuss the broader implications of our project.
In terms of broader implications, IGT can now transition from scanner-based technology to camera-based technology. Also, the software only uses the Java standard library, so like we mentioned before, we use no third-party sources. Also, there will be a patent in the works this May to process raw images. Finally, we would like to announce that we've been accepted to the Capstone Design Conference in New York, which we're very excited about. And we would like to thank our technical director, Frank Mateo, and Dr. Sunak for all of his hard work. Thank you.
Thank you.